Thank you for watching, liking, commenting, sharing, and subscribing right now.
So, I'm John. I'm a grad student at the University of Washington. I don't know how many people heard about the Vocal Joystick. We got a little bit of press a few months back. So anyway, the project, first thing I should mention is this is definitely not just my project. My advisor is Jeff Bilms. He's in electrical engineering. We also work with Richard Wright in linguistics and James Landay. He's a big human-computer interaction guy in computer science. Several other students up there, some past, some still current. And I've done most of this. Me and Xiao Li, who's one of the former students, have worked primarily on the back end, whereas Susumu Harada is the main guy for dealing with interface stuff. And he's doing a lot of fun new research there. I'll try to cover a little bit of it, but most of my stuff, well, I'll cover a mix, just a general overview of things. The other thing I'll point out is that this is exciting for me because as a grad student, most people don't actually care about my PhD research. And here I get to talk about it to a bunch of people who aren't even in my own research area. So you can tell that I'm very much an academic, given that I have an outline for a fairly short talk here. So anyway, what is the Vocal Joystick? It's a device we're building. It's software, but an assistive device for individuals with motor impairments. So this can be either permanent or temporary. We're mostly envisioning it for people who have, say, some permanent injury, say, car accident or Iraq war veterans. We're getting a bunch of people back who are missing limbs, but we're doing a better job at saving their lives by evacuating them quickly. This means there's lots and lots of people who, for some reason, don't have the full use of their hands. And this is a barrier for many of them to using computers. The project is basically an extension of speech recognition research, and that's what my lab actually does. It's primarily speech, natural language processing, and machine translation. So it's based on our experience in speech recognition. But rather than trying to recognize individual words, which are discrete independent objects, we're trying to get smooth and continuous control of various devices. So we're trying to use your voice to replace the mouse, not just a keyboard, as in traditional speech recognition. For those of you who have bad memories of the SAT, I hope this isn't too painful, but there's an analogy of speech recognition to the keyboard as Vocal Joystick is to a mouse. But of course, we're trying to build infrastructure that's more general than just controlling a computer mouse. So right now what we're doing, we plan to expand this in the future. Well, my advisor plans to expand this in the future. I plan to graduate sooner. So if you actually look at what the human vocal tract can do, vocal tract, we're concerned with, yes, the lungs are involved. I'm not going to go into a physiology lesson here, though. Basically just anything, mostly your mouth and lips, and then, of course, whether or not you're using your vocal folds to produce a pitch. So we can do a lot with that, and speech is a very complex signal. We don't actually realize just how much we're doing when we're talking. So right now we have 4 degrees of freedom, and we're getting this by looking at several continuous aspects of the voice. First is vowel quality, which is like the specific vowel you're making. You can look at that as a continuous space of all possible vowels that humans can make, and linguistics characterize this as roughly 2 dimensions. Then there's pitch, which is just what note your voice is at, and loudness, which is pretty obvious. So we're using, for say the computer screen, we're using vowel quality to control the direction. So here's 9 different vowels. The one in the middle, if anyone's wondering why this would be interesting, is if you want to be able to say vary or pitch or loudness without using a vowel to go in a specific direction, you want a vowel that's not associated with directional movement. So when we're using Vocal Joystick on a computer screen, these are the directions. And this is the International Phonetic Alphabet. So I can I don't, is this on? No. That helps. Okay. They have an actual good laser pointer. Okay. So a, o, u, I, a, and a.
Graduate.
I wish it were that easy. And we actually do have, my apologies for anyone who's red-green colorblind and might have trouble with the middle word. I hope the outline is sufficient. Anyway, regional dialects and just accents do affect how you're going to pronounce some of these words. This is about as good as we could get using English. And if you're wondering why did we come up with this specific ordering, there actually is some amount of theory in this, and this is why it was nice to be working with a linguist. So we're using just the theory of how vowels are produced, and you have a couple of things, height and advancement. People used to think it had something to do with your tongue position, it's only sort of, so what those are doesn't actually matter very much. The idea is that vowels that are produced more similarly in your mouth are closer together for control purposes. And what we want to do is allow at least rotation reflection of the current compass that you saw before. And that'll allow a bit more customization so people can be more comfortable. Based on how we're actually recognizing the vowels, we could, in theory, allow arbitrary ordering, but then you break certain properties of the theory. So we're not sure if this would be a good idea. And this is what human-computer interaction researchers are for and not what electrical engineers are designed to research. So I get out of that. Roughly superimposing the compass from before, this is what we're doing. So up is, I guess it helps if I have a laser pointer. Up is down here, down is this way, and then the sides. And now a demo. I apologize for the video quality, but this was done actually just using a regular digital camera to record the screen. Are free flash games you find online fun? So if you notice in any of the video demos I have, I've carefully chosen clips where I'm not the one speaking. Next is, we also have a little robotic arm. The arm itself is from a kit. We did, another grad student assembled it. We did not design that. What we did design is the interface with, between our software and the arm. And this was for a conference submission, so there are titles so that people can figure out what's going on. And given the nice titles, I don't need to tell you. So we have a couple of different ways of controlling it. This is, as the titles were saying, directly controlling each joint, which is not as intuitive to use. We don't grab things by thinking, okay, now I want to extend my elbow, and now I want to move my shoulder down. And if I had a slider, I'd jump ahead in the demo, or in the video. So this one is controlling just the end point of the arm. So we also have a program called Voice Draw, which is much more related to the mouse control. And, okay, I have a cursor on my screen. It's not up there. So using that, you can control things. I believe it's using, for instance, loudness to control brush thickness, the same vowel mapping to control direction. And you can also select colors. This one does more of a mix of vocal joystick control with standard speech recognition, which is something that we haven't done very much of so far. The idea, of course, is long-term to be able to let you use regular speech recognition for dictation or anytime you need to enter text, and use vocal joystick when you need to move the mouse cursor. So this was done by one of the other grad students, the one who designed Voice Draw. And he took about 3 hours to do this using only his voice. I couldn't do this using a mouse or pen, or I just can't draw this ever. And he managed to do it entirely with his voice. For a user study, he actually found a quadriplegic artist down in Berkeley. Unfortunately, the artist has since passed away. But on the left is a picture that he'd done using Dragon Naturally Speaking, which has mouse control, where you can say things like, mouse cursor up, faster, wait a little bit, stop, mouse cursor right, stop. So you have no way to control how fast it's moving with any continuous degree of control. You're required to use their preset speeds. I think they might have 8-way control, but you have nothing approaching arbitrary control in speed or direction. So he managed to do the picture on the left in about 9 hours using Microsoft Paint and Dragon Naturally Speaking. The picture on the right, he managed to do with Voice Draw. It took, the image here is reduced in size. The actual pixel size is much larger than the first piece, and it took him about 1/3 the time. This is art, and it's abstract art, so it's certainly subjective. Most people seem to prefer the one on the right. It allowed him to do what I'd call more interesting lines, rather than the perfectly straight lines that he was more limited to in the previous method. So a little bit about our system. We do not currently have a Mac version, but we do have it for Windows and Linux, and we're trying to get everything in order so that it'll work and we can post binaries online. We're pushing to release source, but my advisor is not completely sure that our code is to the point where he wants other people to see it yet. We have a C++ and C# interface, and just really high-level block diagram. This is sufficiently generic as the first, say, half of it is generic enough to work for more or less any pattern recognition system. So the first thing we do is we pull out just different aspects of voice. Then we try to recognize more general patterns in them, which is pretty standard machine learning. We have our own algorithms, but the general concept. The most novel portion is the third block, which is where we try to do things to, say, decouple different aspects of your voice. It's not very obvious, but for instance, we might think that we're making sounds that are equally loud, but if you just change which specific vowel you're making, the actual energy in your speech will change quite a bit. Just things like the sides of your mouth, depending on how open or closed your mouth is, they'll block some of the airflow and absorb some of the energy. So all these things, when we're listening to other people talk, it doesn't matter. But if the system is trying to estimate things, well, it has to try to explicitly compensate for them. So a little bit on pattern recognition for people who are interested. We have a couple pitch estimators. It seems like a pretty simple problem, and for certain musical instruments in isolation, it is a solved problem. For speech or multiple instruments at a time, actually recognizing what pitch or multiple pitches exist is very much not a solved problem. We also have a couple different ways of classifying vowels. One's just a standard neural network, and then ratio semi-definite classifier. I'll mention a tiny bit more about that in a minute. We also came up with a way so normal speech recognition works much better if you go through an enrollment period, and the same is true for this, although we can get ours done in all of, say, 30 seconds. And then what we're doing, so I mentioned vowel control, and that's what I've mostly focused on. We're not using pitch for, say, mouse control, although you saw pitch control for the little robotic arm. But the speed of movement is based on both the specific vowel you utter and loudness. So the ratio semi-definite classifier is mine. I'm going to show you at least one equation. This is sufficiently novel that I'm going to make it a good portion of my PhD work, and now you've all been exposed to it. So ha. If we have any questions or job offers, I'm happy to listen. I guess there was some interest from Chris in a demo, so demo first? Okay. Okay.
Chris, you try. What? So you should be able to recreate Mount Fuji.
I don't have that one compiled.
I could try.
You can try drawing his own face.
Oh, God.
I'll give a demo first.
Yeah, you do the demo. I may give it a shot, if I'm so allowed.
It'll be this year's Chew on Head.
Well, this will have to be in video if it happens.
That's what this is for.
Oh, you're upgrading.
Okay, I clearly need to move out of presenter mode.
I do have a question. As you're kind of getting set up, just kind of cue the audience. Just ignore me, John. How many of you either have friends or family or know of somebody who could likely use something like this? As expected. So, there's the software. Okay.
Yeah, I had to come out of presentation mode, and I'm sparing you my background.
It makes speech therapy a lot more fun for some kids too.
So yeah, we've thought about trying to do that. The biggest issue we run into now is it works much better if you adapt the model first, which means it's going to base things on how close you are to what you train the system on. We're certainly trying to figure out ways to get a more general purpose vowel recognizer that'll work on everyone, and we're just not quite there. We're getting closer. So I actually am going to show how long it takes to adapt this thing. So it's 2 seconds of each of these vowels, assuming my laptop is not confused and running slow for no good reason. Sorry, you guys already heard these. I apologize. Ooh. No, this one does not really exist in English as something we intentionally make. Yeah, my laptop seems to get confused and just not run at normal speed for this. A. And then we also have a couple sounds you can use for clicks. I thought I commented you out so you wouldn't waste time. So we have several different classifiers, and they take slightly different amounts of time to adapt. You probably want me to have something interesting open, so I can trim down volume for everyone. Is this full screen up there? No.
Yep. Because you're connected to the projector.
Okay, so clearly you can see at this point. Okay, I'm gonna kill it now. So,
one of these days we'll eventually see a 3D interface. I was wondering, what other variable voices
okay, I would have repeated the question. But
one of these days we'll eventually see some need for a 3D interface. I was wondering what variable would you use of the linguistic capacity of our voice box to track that?
Well, so like for the robotic arm, that's already working in 3D. So we don't have full, say, 6 degree of freedom control, but we can get up to, say, 4 at a time. And right now we're using 3 of them, like 3 degrees of freedom for 2 dimensions plus speed control. And we can also add in pitch. Some of the other things, so there are a bunch of research questions that we'd still need to answer. And this is one of the interesting things about working on a project like this, is that like there are we can make conjectures about some things, but it's hard to say in advance. One possibility is that you could do something with modulating, say, your pitch or loudness. And if you can stand a tiny bit of delay so that it can say average and find just the sort of slightly longer window average as you're modulating at some frequency, you might be able to pick up an extra degree of freedom by modulating around a potentially moving average, if that makes sense. So imagine, say, a sine wave of varying frequency around some center frequency that may itself be moving. So things like that. There are certainly, if you're looking at degrees of freedom that aren't necessarily associated with making a pitch, then you can get things, it's called frication. So fricatives, things like an F sound, they're much weaker, but you can change exactly where, so those come from making a constriction somewhere in your mouth. And you can change the exact place reasonably smoothly. But of course, it's harder to do certain sounds like that while you're actually making a pitch with your vocal folds.
Have you looked at optical tracking devices at all? I used to work for a company called Natural Point. We made head tracking devices and all that kind of fun stuff. And they worked really well, but they're very complementary to voice recognition stuff like you're doing here. And I'm just wondering if you've tied those together at all or done any research in that area.
So we haven't, just because we're focusing primarily on developing the voice technology, and we're approaching it from a more academic point of view rather than making a useful product directly. There was an interesting paper several years ago. It came up with a title, Magic Pointing Manual and Gaze Input Cascade, where in that case it was using, say, an eye tracker to roughly position the cursor. But eye tracking isn't all that great for really fine positioning. And so it was doing that and then using a mouse to sort of zoom in from there. You can use your eyes to quickly move around and get gross positioning and manual control for more fine-grained stuff. And so we think this would work really well for something like that, to use eyes plus voice, although you can't come up with quite as nice an acronym.
So what type of pitch detection algorithm are you using, actually? Because I really love speech processing stuff, and I'm really interested in how you got it so close.
Okay, if you want more details, you can find me afterwards. So the default one, it was published sometime in the mid-90s by David Malkin, and the title of the paper we took it from is just Robust Algorithm for Pitch Tracking. Really creative titles in speech research. The basic idea is you take what's called an autocorrelation, basically seeing how well the signal matches up with itself at different shifted versions of itself, and then run dynamic programming from there.
Thank you, John.
Thank you.
Eric, how quick? And you're.
Have you had to put in actual just straight music to it to see what kind of results come out of it?
Wow. Sorry about that.
He had pasta for lunch.
Wow,
thank you, John.
Okay,
Thank you.
so really quick answer. I can answer that very quickly.